La la. La la la. All right. I'll begin with a word of prayer. Dear Father, we thank you again for this day and for these students, this class. Just pray that you'd be with us, help us to glorify what we do, and just understand a little bit more about these topics of from John Lee's book, and just help me to talk about the interesting part and not the uninteresting part, Lord. In your name I pray, Lord Jesus. Amen. All right, so we were talking about chapter, let's see here, chapter 19, which is on distributions and involutivity. So, the bigger topic, of course, is Frobenius Theorem. So we'd like to talk about what that is and what it tells us. And so I suppose we do need to just rehash, like, what is a distribution? Distribution D is a subbundle of Tm. Locally, you could say something like D is the span of, x1, x2, xk, right? So these, all vector fields, aka sections of D. So a section of the distribution is just a vector field which can be built from like a linear combination of vectors in the distribution. All right. And if that's the case, then x1 through xk, if that's a frame, right, if it's a pointwise linearly independent set of vector fields, then that's said to be a quote unquote the distribution is locally spanned by those vector fields. And this is a so here I'm talking about a rank k bundle, or a rank k, let's say a rank k distribution. All right, so I gave you guys the big words last time, involutivity, right? And so let's rehash that again. So definition, the distribution is said to be involutive if let's see here how to say it. Well, there are various ways to say it. All right, here's what he says on page 492. He says D is involutive if given any pair of smooth local sections of D. Then, so here we go. If we have x and y smooth local sections of D, then the Lie bracket of x and y is also a section of D. All right. This makes D involutive. All right. Now we had another definition, which was integrable. A smooth distribution D on M is said to be integrable if each point of M is contained in an integral manifold of D. Definition: D is integrable if each P and M is contained in an integral manifold. Well, I should say submanifold probably. Manifold is good enough. Integral manifold of D. I guess that begs the question, what on earth do we mean by integral manifold of D, right? So what was that? What's an integral manifold of the distribution? He defines that back on page 491. He says that a non-empty immersed submanifold N of M is called an integral manifold of D if every tangent space to the submanifold is found within the distribution. So integral submanifold, it's an immersed submanifold, basically N a subset of M, such that the tangent space at P to N is an element of the distribution at P for all P in N. So this makes it, if it's integral submanifold of the distribution if its tangent space aligns with the distribution, all right? That's all that's saying. Excuse me. All right. And so let's look at some examples. All right, so here's the examples. So this is 19.1, if you're wondering where I'm getting this. Page 491. So example A, if V is a vector field on M, V identically not 0, all right, so a non-vanishing vector field, then V defines a one-dimensional distribution, all right? A smooth rank 1 distribution, so like D, you just a span of, span of V, which is kind of dumb, right? Like dP, what would it look like? It's just like, essentially the set, what's in there, like constant times V sub P, right? Such that C is a real number. So it's a smooth distribution of tangent lines, right? The integral submanifold to this would just be what? What would an integral submanifold to this distribution be? We have another name for it. We've talked about it already. Let me not put the span here. Let me just say D generated by this.
What's the difference?
The difference maybe would be that I'm tempting people to think that they're constant linear combinations of the vector fields, but it's only done pointwise. So like, I could have a section of this that was built from things like a smooth function times these, as long as it still lands each point in the subspace of the tangent space of Rn, which is spanned by these guys. So the coefficients don't have to be constants. When I write span like that, it makes me think of constant linear combinations, so maybe that's not the right notation. Did you guys got the answer for part A? What are the integral submanifolds there for this guy?
Integral submanifold is
The tangent space. So it's a one-dimensional. I mean, so like, so the integral submanifolds can have any dimension up to, but not past the dimension of the distribution if you think about it logically, right? Like if you had a 5-dimensional submanifold and your distribution was 3-dimensional, you can't fit a 5-dimensional tangent space inside a 3-dimensional distribution. So by dimensionality, integral submanifolds to a distribution can be at most the dimension of the distribution, but not past it. Here, this is just a one-dimensional distribution, so you only have one choice. One-dimensional manifold, aka curve. What's a curve that aligns with a vector field? What if I had V at gamma of t, right, equals to d gamma dt, or gamma prime of t if you like, right? That's a what? That makes gamma what kind of curve to V? Smooth? No. Uh-oh. Uh-oh. Oh boy. Let's see here, to use the vernacular of your generation. So it's an integral curve. You guys are killing me. Integral curve. This is what we called it, right?
Velocity vector is equal.
Yeah, exactly. The velocity vector of the path matches the vector field. That is a particular instance of the integral submanifold. So this notion of integral manifold is a generalization of the concept of integral curve. Basically, it's like a higher dimensional extension of that. Now here, if you have these guys, that defines a rank k distribution in Rn, all right? All right, and what do the integral submanifolds of this thing look like? Oh, maybe. Well, I guess my question is like, let me see here, how can I say this? How about this? If I was to parameterize these, I could do like what? I could do like something like, oh, I don't know, I don't have a good name for parameterization. Let me call it psi. All right, so psi of, say, x1, x2, oh, sorry, my indices are down all of a sudden. Let me fix them. x1 through x2 through xk, right? Those are my parameters to describe the submanifold, and I would just map those to x1, x2, xk, right? And then what? If you like, I could put a constant here, let's say, constant vector, right? And just fix the constant vector here, where this constant vector has how many components? It's got like, yeah, C1, C2, Cn minus k. So this would be the image, so like psi c of Rk would equal to n, which is an integral submanifold of Rn. That would be a description of the integral submanifolds to this distribution. Now, this is not how John Lee describes them. He has the good sense to describe them in terms of equations instead of parameterizations. I used a parameterization, right? So this is actually the inverse of the chart on the manifold, right? If I took a typical point in this and I take the inverse of it, I would just give you back these guys, because you can use the first k Cartesian coordinates as the coordinates on such a manifold, submanifold. It's a kind of silly one, right? In terms of equations, n is equal to what? It's equal to x1, x2, xn, such that what? Such that, like, x upper I is equal to c upper I for I equals, oh man, I can't do math. I need to do what? Thank you. I plus k. Oh, man. Woof. Oh, here it comes. Nah. I equals 1 to n minus k. All right, so there we go. Excuse me. All right. A very boring, but perhaps useful example just to sort out some ideas. See, because you guys got to be aware of this issue. This is always an issue. We can either describe a submanifold in terms of equations or in terms of a parameterization in Euclidean space. We always have these two options, you know. All right, so next example, C. C here, he says R distribution on Rn without 0, all right, spanned by the unit radial field. And so here's an instance of summation. So let me just call it V equal to the sum I equals 1 to n of x upper I partial xi. So that's the vector field he has in mind here. He calls it the unit radial field. All right. So what's the distribution? What's the dimension of that distribution? So I mean, it's a single vector field, right? So it's again a rank 1. All right. And something else that we could do is we can define our perp to be equal to, like, you know, W, such that, you know, W dot V is equal to 0. You know, and I mean that, of course, pointwise. This is the complement, the complement to the radial distribution. So what's the dimension of the complement? Rank not 1, but not 2.
0.
You got to be a lot greedier, a lot more greedy. N is too much. Went too far. N minus 1. Yeah. So what does it mean for two? What does it mean for two distributions to be complementary? So like a distribution R1 and a distribution R2 are complementary if R1 direct sum R2 is the whole deal. So like complementary subspaces are ones whose sum is everything, but they are independent. So for two subspaces, complementarity just assumes that the sum is everything and the intersection 0. Now, admittedly, the definition of like complementarity, well, I don't know if complementarity is even defined for 3 things, now that I think about it. But independence of subspaces is more subtle if you have like 3 or 4. But if you don't know about that, you should read about it sometime. But okay, so anyway, focusing here, that's a rank n minus 1 distribution. Okay, so let's just narrow the focus a bit. Let's do n equals 3. What's this look like? So we've got V is like x partial x plus y partial y plus z partial z, right? And what's the perp to this? Could be something like maybe span. Oh, well, see, span is dangerous, but our perp generated by, how about this? Like x partial y minus y partial x. That, when you dot product that with V, you get 0. What else? How about same trick again, but z partial y minus y partial z, right? This dot product with that is 0. but by the dimensionality, there you go. That's a local basis for the complementary distribution. What are the integral manifolds for these distributions? I'll do it for n equals to 2 where I can draw the picture, okay? So n equals to 2, you've got v is x partial x plus y partial y, and, I'll just call it v perp is y partial x minus x partial y. That's perpendicular to that. These give a distribution on the deleted plane, and it's easy enough to know that these are the integral curves of v. What are the integral curves of v perp? So they're just circles. Etc. These would be the integral curves of the v perp. Both v and v perp in this instance foliate the space in the sense that every point in the space is covered by one of their integral submanifolds, right? And actually, they're very nice. I think they fit the description that's given later on in this chapter. So let's get on with it. Example D is finally a not nice example. And this is the fundamental not nice example. So here we have D spanned by, right? And what that means, guys, is that D sub P is literally equal to the span of X sub P, Y sub P. It's just I cannot commit to the same constants at different points. That's why we're being kind of cagey about saying span. All right? Yeah. I suppose if you wanted to extend your notion of span to like smooth vector fields, you probably could just say like span over the ring of smooth functions and it'd probably be fine. Anyway, so here's the X. X is partial X plus Y partial Z, and Y is partial Y. All right? And he says, it turns out that this has no integral manifolds. All right? He says, because x and y are tangent to n, any integral curve of x or y that starts in n has to stay in n, at least for a short time. Thus, n contains an open subset of the x-axis, which is an integral curve of x, and it also contains, at least for sufficiently small x, an open subset of the line parallel to the y-axis passing through x, 0, 0, which is an integral curve of y. Therefore, n contains an open subset of the xy plane. However, the tangent plane to the xy plane at any point p off the x-axis is not equal to d sub p. Therefore, no such integral plane exists. I will foolishly attempt to recreate the picture. Very foolishly. All right, I'm going to regret this, I guarantee you. All right, so what he does is he's drawing little planes to illustrate like the local span of x and y. So at the origin, you've got like a little plane like this, a little plaque like that, and down here you've still got a little horizontal plaque like that. All right, but if you go back a bit, then it drops down below the origin. All right, it drops down below the origin there. And if you go a little bit over here, it actually comes a bit above the xy plane. All right, so like, let me foolishly try to color in these. And similar down here, if like you look at these ones, it's going above the xy plane. So let me draw the actual sort of span. If you can imagine like linear combinations of x and y for like small values based at these points. Let's see here. So the claim was there's no integral manifold. I think I've done. Does the integral manifold have to have the same dimension? Oh. It's not just that TPN. I'm not. Something I said earlier today is wrong. It wasn't that. Here's the problem, guys. Let's go back. Let's go back. I said something unfortunate. Not even politically incorrect either. Disappointing. Just math. This is not element of. This is equals to. So I was wrong. It is not acceptable to have integral manifolds, submanifolds of dimensions 1, 2, up to k. No, it has to be full dimension. Integral submanifold fills the whole distribution with its tangent space. All right? So like, it had to be one-dimensional. Of course, that didn't hurt us in our previous discussion. It's just that if I'm dealing with a rank 2 distribution, I need to find a surface which takes as its tangent space the distribution. You know? Okay, so oopsie. So that's why over here we're in trouble. See, because I was starting to get confused, because I definitely can find integral curves, right? Like for instance, if you just take, well, as I was just reading from Lee, you know, the x-axis, right? That's an integral curve of this guy, because, you know, you can just look at like gamma of t equal to, like t 0, 0. This has d gamma dt equals to, partial x. And then plus y partial z evaluated at, t 0, 0. See, this term is gone because it's 0. So but it is true that this is equal to x of gamma of t, So therefore, this path is integral to that particular subset of the distribution. And likewise, the y-axis is integral. And not just that, of course, you can take like any, oh, goodness gracious. So like any line like this, right? Any line that's just purely in the y direction, doesn't matter where you stick it through, that's an integral curve to this. So the bigger idea is, for this to work together, it has to be somehow that these integral curves can be sewn together, like put together, and somehow give you an integral surface, which is all fitting in the tangent. But the problem is that if you could imagine an integral surface here, right? It would have to be both like below the tangent plane over here and above it over there, something like that. I don't know. Maybe you guys can see it better than I can, but every so often I convince myself of this picture and why it breaks it, and then I talk myself out of it. So eventually I'll get over this hurdle. I'm just not quite there yet. But he says that this last example shows that in general integral manifolds may fail to exist. And he's got a proposition to give us a help on that. Proposition 19.2, which says that so you have a distribution, smooth distribution, and sections of the distribution, subset of the sections of the manifold, all right? Well, this is, smooth sections on D, okay? Which is just a fancy way of saying smooth vector fields who take their values in D. Just like chi-m is smooth vector fields which take their values in Tm, okay? Well, anyway, here's the punchline. Then D is involutive, all right? If and only if gamma of D is Lie subalgebra of chi-m, well, whatever that is. We've agreed to not know what that symbol means. So it's a Lie subalgebra of the smooth vector fields on the manifold. And Lie subalgebra with respect to the Lie bracket here. That's the algebra structure we're talking about. So if you believe this proposition, all right. What's that? If I believe it. The proof belies the proposition. It's page 492. It's right there. But anyway. So what happens here? If you calculate the Lie bracket of these two guys, what do you get? So if we calculate like x, y, f, we've got, x of partial yf minus y of partial xf plus y partial zf, which is equal to partial x, partial yf, plus y, partial z, partial yf, minus partial y, partial xf, minus partial zf, minus y, partial zf. I did the product rule in that last term. So some of these things cancel. They'd be canceling like that and that because the partial derivatives commute. Again, the partial derivatives commute, but we have a winner right here. So we've got minus partial zf, right? So therefore, the commutator, the Lie bracket of x and y is minus partial z if I haven't made a stupid mistake. Right? But the thing is, that's not in the distribution. Right? You're like, well, but there's this. Fair enough, there's that, but can you just produce a single lonesome partial z in this distribution? You cannot. There's no way of adding and subtracting junk here to isolate partial z like that. It's simply not in the distribution. Therefore, this distribution is not involutive, and that leads to the fact that you can't find actually an integral submanifold. Of the distribution. And again, if you don't quite understand the picture and why that proves that you can't, I feel for you. I'm right there with you. It's just I'm not the best at that kind of visualization. Proposition 19.3 says every integrable distribution is involutive. All right, let's go on here. Lemma 19.4 says that if you have a distribution, you can check involutivity on a local frame. It suffices if you have a local frame that spans the distribution, if you can check that the frame is closed under the bracket, then you've got involutivity. So, and then that brings us to the alternative viewpoint, which is differential forms. So, guess I'll do that over here. By the way, the proofs I'm skipping, they're not that hard. You probably can understand them if you read them. And you might need to read them to understand how to do some of the homework. So just a warning, okay? All right, so here we go. This is lemma 19.5. It says, suppose M is a smooth n manifold and D is a distribution of rank k. Then D is smooth if and only if, at each point P, M has a neighborhood U on which there are smooth one forms. Smooth one forms. And we call those omega 1 through omega n minus k. And let me just write the punchline for us. The punchline is that the distribution at the point Q can be written as the intersection of the kernel of the one forms. Omega 1 at the point Q, intersection with the kernel of omega 2 at the point Q, intersection with the so there's n minus k one forms. You have n minus k one forms whose, let's say, mutual kernel defines the distribution at the point Q. All right. And if you look at the proof that's on page 493, it's essentially using like the dual basis idea and extending the local frame, these kinds of things. It's, excuse me, not too bad. Now these things have names. So these are called the local defining forms. Local defining forms for D. So we got two choices. We can either express D in a positive sense as a local span of k vector fields, or we can describe it as in a sort of a negative sense by describing n minus k one forms which annihilate things in the distribution. And here's another definition. Omega, a p form on M. So this notation means differential p form on M, guys. This is said to annihilates. It annihilates D if whenever we feed it local sections, p local sections from D, we get 0. All right. And he says, in the case p equals 0, only the 0 function annihilates D. Okay. This brings us to lemma 19.6. Lemma 19.6 says, suppose M is a smooth n manifold and D is a rank k distribution. Take these smooth local defining forms that we were just talking about, an open subset. Then a smooth p form on U annihilates D if and only if it can be expressed in the following form. So let's just say omega as above if and only if the following. There exists smooth P minus 1 forms. P minus 1 forms on, so this is all with respect to an open set, right, with an open set U. So open subset of M. So there exists P minus 1 forms on U, namely beta 1, beta 2, beta, how many do I have here? N minus K, such that what? Oh man, rats, not omega, phooey. Hey, let me fix this, guys. I gotta make a little bit of a correction here for the sake of not writing much. Eta? Eta. Eta. A? There we go. And here's the deal. Eta equals to the sum I equals 1 to n minus k of omega I wedge beta I. All right. So that's the situation. A p-form on your manifold will annihilate the distribution only if it can be constructed as the sum of wedge products with the local defining forms, right, whose mutual kernel defines the distribution, and these other smooth forms, beta I. Now, let's go back to our example. Let's go back to example 1 and see if we can maybe what is, can we all right, so oof, yowzers. I'm not sure I want to think about I'm not sure I want to think about A. Because to describe A in terms of the differential form description of the distribution, I would have to produce n minus 1 defining 1 forms. That seems like a hassle. I mean, maybe you could do it, I don't know. It's probably not that hard. All right, I'm going to let it go. What are the defining 1 forms for this example here? D is equal to the, kernel of omega 1 intersect the kernel of omega 2, right? Intersect the kernel of how many do I need? N minus K, right? So what's my omega 1 equal to? What's my omega 2 equal to? What do you want to use here in this one? What differential? What 1 form will automatically annihilate all of these? Let me remind you of your test. dxi partial xj is the Kronecker delta. Right? So if I want something that will annihilate all of these, how about? Yeah, but not partial. It's got to be 1 form. So I take your partial and raise you a differential. dx k plus 1. That annihilates all of these. And once you get started, it's easy to keep going, right? dx k plus 2 and so forth and so on, right? Eventually we will get to omega n minus k equal to dxn, right? So the local defining one forms here are simply the coordinate differentials. And all of a sudden that lemma I just wrote seems rather unsurprising. For a p form to be annihilated on this distribution, it has to be built in such a way that there's no term in the p form which does not involve the defining one forms. For instance, if I had eta equal to, let's say, dw wedge dz, and my distribution was, spanned by partial x and partial y, and I was just in like here's a four-dimensional example, right? Think about that. If my two form was dw wedge dz, and I'm talking about R4 with coordinates x, y, z, w, all right? That would not be annihilated. That would not annihilate the distribution. I'm trying to see how's the theorem saying. It's in eta annihilates d if and only if when you feed it sections it's 0. Maybe mine might still might be 0. I don't know. Oopsie doopsie. Let's see here. How can I do it? Oh, maybe it's not so easy. Let me shut up. I'm no longer convinced by my example. Let me erase that from the record. Sorry, guys. In the best of all worlds, I would have had an example ready to add to the book here. Sorry about that. Okay, so and then we get theorem 19.7. Theorem 19.7 says the following. I'm going to erase this right here and give us a, I guess it's fun to think about what what's the annihilating. One other thing. Let's not leave this discussion just yet. Let's leave my ill-fated attempt to find an illustration of the lemma, but let's go back to the defining one forms. There's some really low-hanging fruit here. Like, how about this one? So if, rats, I guess, if you guys remember my homework problem where I defined the hyperspherical radius. So like the equation for the sphere, the n sphere in Rn plus 1 is just the hyperspherical radius equal to 1. So like the hyperspherical radius is like the square root of x1 squared plus x2 squared plus da 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 plus xn plus 1 squared. So for that radius, this, we could have our perp is simply the kernel of the differential of the hyperspherical radius. And just one will do because this is a rank n minus 1 distribution, so it can be defined by a single defining one form. Because here k is n minus 1, so n minus k is just 1. So you just need one form. And of course this sort of marries with your intuition nicely because the integral manifolds, right? See, if this is a very nice case because in this case you can literally get the integral manifolds by integrating. Like the integral manifolds for this example are literally r equals to r. That is your typical integral manifold for our perp, which we can easily and intuitively derive from the differential form perspective. Whereas that would have been a monstrous calculation if we took the distribution perspective in terms of vector fields. You'd have n minus 1 of them. Stupidly easy in the differential forms perspective, technical in the vector field perspective. So there's that one. This one here is the kernel of d theta. This one is the kernel of dr. Again, the integral curves can literally be integrated from the single defining one form because of the dimensionality here. It's super nice. Integrate d theta, theta equal to a constant. Those are the rays from the origin. Integrate dr, r equals to constant. Those are the circles. So see the differential form description of these. It's especially nice when there's just one defining one form, which is only the case for like spaces of codimension 1. Excuse me. All right, enough of that. Anyway, so next up was the theorem here. One-form theorem for involutivity. D is involutive if and only if the following condition is met. Oh man, I need to, well, I think we're done with this pesky example here, so I'm going to erase it. Oh, look at this mess. Look at this mess. All right. Let's see here. So this one is eta. Any smooth one form that annihilates D on open subset U of your manifold, then d eta also annihilates. Thanks. Annihilates D on U. And the full statement here is from the previous page. So D, a subset of M, D is involutive if and only if the following condition is satisfied. So D involutive if and only if this here criteria is met. Ah! Who put that there? Well, you warned me of it last time. Then I gave you guys a test, so I understand. Got it out for me now. It's understandable.
I think you gave us the test before.
Oh. Really? Before I wanted you. Is that right? Oh, because we had a. Did we have a class after the test? Oh, see, I felt like it was like last class. Oh man, I'm taking forever to grade this test. I'm sorry, guys. Okay, so I think the proof of this is actually instructive a little bit. So first, we'll assume that D is involutive. All right. So we'll look at this direction of the proof at least. Assume D involutive. What does that mean? That means that the Lie bracket, right? The Lie bracket of two local sections is again a local section of D, right? Okay. And then he says, all right, so we're going to assume D is involutive. Now suppose eta, annihilates D, all right, on some subset U of M, all right? He says then, for any smooth sections x and y of D, right? Check this out. We can go back to our exterior derivative formula. So d eta of xy, what is it? Does that make sense? Eta is a 1 form. The exterior derivative gives us a 2 form, right? And the formula for the exterior derivative of a 2 form acting on a pair of vector fields was simply as follows. It was equal to x of eta of y minus y of eta acting on x, and then minus eta acting on the Lie bracket of x and y. All right, great. But what did we just assume about eta? Eta annihilates local sections, right? So that makes this 0, it makes this 0, and this right here is again an element, that's a local section of D. Well, how do I know that? That is by assumption of the involutivity. Involutivity tells me that the bracket of x and y again is a vector field in D. But then by assumption, eta of that is 0. Altogether, it's 0. But x and y were arbitrary. Therefore, d eta is an annihilator of the distribution. Yeah? How about the other direction? I probably should just stop there because that feels right. I'll mess up the other direction somehow or another. All right, let's try. So what are we supposed to do? The other direction, we're supposed to assume that this holds, right? Assume that this implication holds. And we're going to try to show that implies D is involutive. All right, so so let x and y be smooth sections of D. And omega 1, omega 2, omega n minus k are local defining 1 forms of the distribution, right? We know those exist. Then what? Then 14.8 shows, 14.8, what's 14.8? I don't have my book. Oh well. So we can calculate, well, okay, so here's what it is. Omega I acting on the Lie bracket. So 14.8 is the section on is the chapter on differential forms. So this is one of the formulas that we had for how a differential 1 form acts on a Lie bracket. It turns out this is the formula for it. I think this is actually just writing this formula up here in a slightly different order is all. This is an identity that d eta is equal to that. So if we apply that to the case that eta is omega I, we have the following. So we have x of omega I of y minus y of omega I of x minus the exterior derivative of the I defining 1 form acting on x and y. All right. Now he says that that's equal to 0. Why is that equal to 0?
What's the last term? X, y.
Let's see here. So these are smooth, local defining 1 forms, right? So by assumption, again, 0 and 0. Why is this 0?
Well, I mean,
So my question, let me ask a leading question. What are we assuming in this part of the proof?
DWI, or D omega I is also an annihilator.
Oh, right here, right? Because omega I is a smooth form, and 1 form which annihilates. Therefore, its differential must also annihilate by assumption here.